in this video on thinking about the attenuation of noise in chemical measurements using instruments to acquire those measurements. And so a couple of concepts that we're going to cover today include finding noise in signal, hardware methods for noise attenuation, and also software methods for noise attenuation. So hardware methods, of course, being sort of as you're taking those measurements, and then software sort of post hoc modulation of data. So if precision is limited by electrical noise, which in a lot of instruments, that is the limiting factor for precision measurements, the relative amount of noise can be decreased to the point that other factors limit precision. It's hard to do, but it's possible. But in order to do it, you have to know sort of what your sources of noise could be, and then do a little bit of troubleshooting to find them. So let's do an example. So for a luminescence or emission spectroscopy experiment, you might have some amount of variance that is total, right? All of the variance added up for your measurement. So this would be your total noise, okay, from all sources. This is a function of two sources, basically. The analytical signal, so I'm going to give it a subscript S. So noise that's coming from the analytical signal itself, and any noise that's coming from the background. And so let's break these two things up a little bit and see how we can troubleshoot sort of where noise is coming from in our experiments. So if we think noise is coming from the analytical signal, right? So the analytical signal, a couple of sources of noise there would be, one example would be shot noise. So the S is for shot, coming from the analytical signal. So there's two S's there. So shot noise, the square. The other would be flicker noise. So flicker. So if you go back to our previous video for this week, shot noise is that ejection of an electron across space when it's not supposed to be happening. And then flicker noise is that thing that we can't really characterize so well, but we know it has an inverse dependence on frequency. So there are two sort of variations of where noise could be coming from within your analytical signal. The other spot that you could look for noise would be in your background, right? So if I'm going to go this way with this guy, so background, let's see, give that BK. BK has a couple of sources of noise as well. So it could be background from your sample. So in the form, if you were to put some sort of blank sample on your instrument, one source of error could be from or noise could be from your background sample itself. The other could be dark current. So total dark current. So the difference between these two is that this guy would be without the presence of a source. So if I go back to see the original diagram that we had in the very first video, where we said we need some sort of source that gives us some energy so that we can examine our system of interest and then have some sort of readout, right? With a transducer in there. So this would be our system of interest. Dark current would be if you didn't have a source, but you have electronics that are working in this area over here. There's going to be some amount of current or dark noise that will, total dark current that will come from this sort of part of your instrument without a source. Okay, so that's this guy over here on the right. The other option is if you do indeed have a source, right? If your source is hooked up, but you have a blank sample here, so there's no chemical, the background is everything that's happening without a chemical of interest in your system. And so those are the two differences here. And so you can see how we can start to pull apart where noise might be coming from in the system. If you think it's coming from general background, this could either be shot or flicker noise, right? Similar to this guy over here. If you have, if you think it's dark current, if it's coming from the back end of your instrument, a couple of options for you to think about. It may indeed, so I'll draw this one out. It may indeed be dark current, okay? It could also be something like noise in an amplifier readout. So one of the things that usually happens here is you have some sort of amplification of signal before your instrument will display a number for you, right? So some sort of amplification, and in that amplification, of course, there's noise inherent in that process of amplification. And so you might have it there. You might have, if you think it's dark current, you might have, oh, that is terrible here. Hold on, let me change that. You might have either shot or flicker here as well. So if it's dark current, it could be shot. It could be flicker in either of those, right? So there are a couple of different, you can see how we can start to sort of piece apart where noise might be coming from. So this is all fine and theoretical and dandy, but I want you to think about how we might actually try to troubleshoot some of this in the lab. So it makes perfect sense that the strategy for signal to noise optimization, i.e. troubleshooting noise measurements or noise magnitude in your measurements, depends on what the limiting noise source is in the precision or accuracy of your measurement. And so let's walk through sort of what that looks like. So in the lab, if we're troubleshooting, you're going to be able to measure the standard deviation of the total signal. Okay, and so this is this is like the entire instrument measuring the analyte of interest in a real sample. Okay, so that's the standard deviation of that measurement. And you're going to be able to measure the standard deviation of a blank measurement where there's no chemical of interest, right? So if the standard deviation of your total signal, right, so the total RMS noise, so I'm going to call this T for total, if that noise is not equal to the noise inherent in the blank, then you know that you have some amount of noise coming from your analyte of interest. That could be chemical noise, shifting equilibria, inconsistent laboratory conditions, etc. It may be shot noise from your instrument. It may also be flicker noise. Right, these two are from your instrument. In particular, they're from the electrical circuitry those are going to be hard if you're just a technician in a lab. Those are going to be hard to eliminate. If you were a instrument manufacturer and you were thinking about what materials to use inside the instrument, like that would be the time to think about shot noise and flicker noise. Okay, so let's say that you measured the standard deviation of the total signal, and then you measured the standard deviation of that blank. So if the total deviation or noise is about equal to the noise in the blank, then, which is fairly common with low analyte concentrations, or particularly when analytical signal is small, then you can think about signal coming from either the blank, right, or the dark current, similar to how we talked about up here, there being a blank and a dark current. Okay, so if I have noise coming from the blank, okay, this means that when I measure the noise of the blank, okay, I'm going to look for noise in the background. And I'm going with the same example that I had before. We're just looking at sort of like a luminescence or emission experiment, or spectroscopy experiment. So you could look at a spectra away from a wavelength of interest, or something similar, to look for noise in the background. Again, it might be chemical noise, right? So this could be noise from your solvent, anything that's a chemical that's not your chemical or your analyte of interest that you're trying to measure anything about. So this is a chemical probably coming from the matrix of your sample. Could be shot, could be flicker. Again, these two are going to be hard for you to eliminate if you're just a tech running a method in your lab. But if it's this guy, that's certainly something you can attenuate. If you have blank, if you have if you have noise that is about equal to, noise in the blank, yikes. Noise in the blank, it's about equal to what you see for noise in dark current. Right, this is like the thermal Nyquist noise. This is sort of the end of the road for you. This is where instrument noise is limiting to your precision. So there are a couple of ways that you can sort of work with shot noise and flicker noise, and we'll talk about those in a couple of minutes, in terms of attenuation post hoc, post data collection. But if you're here in dark current, this one's hard to deal with in that way. Okay, so a couple of different ways that you could practically use this info in the lab. So let's talk a little bit about how we can reduce noise. There are some hardware options for you. You can use grounding and shielding, which reduces environmental noise if this is a problem for you. So shielding consists of a surrounding a circuit, or the most critical conductors in a circuit, with some sort of conducting material that's attached to earth ground, right? So that that grounding wire or shield absorbs the errant electromagnetic radiation rather than the enclosed conductors that we don't want to have that noise present in. So grounding and shielding is something that's really common in spectroscopy measurements. Another option for hardware, and so let's back up a minute. What this really means is it's like an actual shroud, metal shroud, or connecting ground wire to any circuitry within your instrumentation. Okay. Another option for hardware modulation of or attenuation of noise is using analog filtering. So this is a really common method of improving the signal to noise ratio in instrumental measurements, usually using a low pass filter. So let's talk about what that actually looks like. So A low pass filter is an RC circuit that attenuates high frequency noise while passing low frequency noise. So on the image to the right, notice I have frequency on the x-axis, right? So anything that's low frequency, i.e. on the left side of this plot, is going to pass through. So I have a, the signal here is high, and then as we increase frequency, the signal decreases. So we're going to let through low frequency things, i.e. low pass, and high frequency things are going to be filtered out. Okay. Generally speaking, the noise that we are concerned with in analytical measurements are relatively high frequency compared to the frequency of our acquired data in general. A high pass filter, it does the exact opposite thing. So anything that's high frequency, so on this side of the plot, goes through. There's high passing of that frequency signal. And anything that's of low frequency gets shielded out. So an example, if the original signal is up here at V sub I, the y-axis of the first plot at the top, and we're talking about time on the x-axis, you can see, right, that the low frequency component of this waveform goes like this, whereas the high frequency component is the one that's so variable, like this, right? So this would be a theoretical diagram, right, of an RC low pass filter. So this is an RC low pass filter. And so what happens is that low frequency component, so that's the one that's in green, passes through no problem, right? So you still see that general waveform. It looks kind of like this. But what we've done is we've gotten rid of much of the noise that used to look like this, right? So we got rid of that. See you later. And now I have this relatively smooth waveform. Right? So this is the effect of a low pass filter. If you were to apply a high pass filter to the same original plot of data, instead of retaining the overall shape, you would have something that instead looked more like this, right? Where we just had really frequent. So this is the time axis, of course. This would be the modulated circuitry. You would lose essentially that low frequency change, and instead would keep the high frequency change, right? So you'd have a flat line with a lot of frequent ups and downs that are apparent in this original plot. All right, so the next thing I want to talk about is modulation, right? So modulation is one of the ways that we can attempt to deal with low frequency noise in samples. So remember that we said that high frequency noise is relatively easy to deal with. It's there, and we know how to deal with it in lots of in most analytical measurements. The low frequency stuff is the stuff that's hard to deal with, and so one way that we can deal with it is through modulation. Okay, so let's talk about what it is. So we can say that direct amplification of low frequency signal is particularly troublesome when an instrument exhibits amplifier drift and flicker noise, which is of course inversely dependent on frequency of the signal being taken. So low frequency signals from transducers are usually converted to high frequency, and then in that process called modulation. So it's that conversion from low frequency to high frequency of that sample in order to filter out some noise, and then modulation back to the original frequency range. So let's sort of see what that looks like. In this diagram below, notice I have frequency in a relatively low range. This is the blue line is my analytical signal. On the y-axis, I have signal power. Notice that it's pretty low. what I'm going to do is modulate to a much higher frequency. So again, frequency on the x-axis, and notice that my signal, which is this peak right here, is now, instead of in the millihertz range, now up in the hundreds of hertz range. The usefulness here is that we're getting rid of any sort of noise that relates to increasing the magnitude of the signal. So the signal is relatively low. If we actually want to measure it quantitatively, we are going to want it to be a little bit higher. And so the way that we do that is to amplify the signal. The problem with that is that it introduces all of this low frequency noise down here. And so we amplify the signal when it's been modulated to 400 hertz, then we don't have to worry about the increase in low frequencies in noise, because we can just use a filter, a high pass filter, right, to pass this guy through without with removing the rest of this. Okay, so we'll modulate up to 400 hertz, then you'll amplify that signal. That amplification process provides all of this noise that's over here. We get rid of that by filtering, and then we can demodulate back to our original frequency range. And the result is that we have a much higher signal that's easier to quantify. So you have better precision, better accuracy in those measurements using modulation as a technique to get rid of noise. Okay, hopefully that rambling made sense to you. Let's talk about how we actually do this in instruments. So one really sort of low tech but effective way to do this is to use a chopper. So a chopper interrupts the light beam. So we're talking about a spectroscopy measurement here, and I'm pretty sure in the next slide I specifically talk about flame atomic absorption spectroscopy. So bear with me if you're unfamiliar with spectroscopic measurements. But a chopper interrupts a light beam, source light beam, periodically by physically blocking it. And so the radiation passed alternates between full intensity and no intensity. So if I want you to think about what that actually looks like. So here's a source, right? Let's call it a laser, let's call it a light bulb, whatever it is. You're going to have some sort of chopper here. So here's my chopper on its stand. Okay. And the beautiful thing about a chopper is that it's going to modulate the signal. So the signal that actually, so then you're going to have your readout device. Okay. So the signal that actually comes out is going to alternate between no signal, 0, and full signal up here, whatever that value lies, right? So you're going to modulate because and it should be relatively consistent, very consistent, in terms of the height and width of these of the square sort of waveform. And the benefit here is that we are putting the analytical data, which of course is the magnitude of these square waveforms, into a higher frequency range than it originally was. Okay, so then we can get rid of some noise here. So let's talk a little bit about what that looks like. All right, so here's an instrument schematic for a flame atomic absorption spectrometer. It has a light source. Okay, light source. It has a chopper right after that light source, right? So this should match up with what I just was saying, hopefully. The next thing that happens in a FAAS is, of course, you need the F, the flame. You will have a wavelength selector and transducer. So this is so in your flame cell, right, this is where your metals of interest, or analyte of interest, lie. They will absorb a particular wavelength of light from your source. And so what you're doing is measuring the intensity of the light of that particular wavelength of light, thus the wavelength selector, after it has gone through the flame cell. So this had some original power, and you're going to measure here an attenuated power. Okay, and so that signal, because you have a chopper, is going to come, that amplitude of that signal is going to be proportional to this attenuated power of your light source. And the waveform is going to, the square waveform that you have is going to increase the frequency of your signal so that you can reduce noise. Why? Because you absolutely have to amplify this signal. And remember that we said when we try to amplify a low frequency signal, we end up with some pretty noisy, not so great data. And so that high frequency modulation of your attenuated power, light source power measurement is going to allow you to amplify that signal to get that which nicely results in a sinusoidal wave, in order to actually make quantitative measurements on this metal. All right, cool. If you've got any questions for me, I'd like to hear about them. But of course, this is a little bit, when we talk about spectroscopic measurements, we'll talk about FAAS. So if this schematic scares you, don't worry. We'll get there actually next week. Okay. So that's what I've got for hardware methods of noise attenuation. There are also software methods for noise attenuation. These are increasingly common, and it is actually really nice to know. A lot of times multiple methods will be available to you in the software that you're using for your instrument data acquisition of your instrument. And so it's nice to know how they work so you can make the best choice that makes the most sense for the data that you're trying to acquire. Okay, so we're going to talk about 2 or 3 different kinds of noise attenuation that can be done post data collection. So the first one I want to talk about is ensemble averaging, and this is as simple as it sounds. Okay, so basically all you're doing is you are averaging multiple sets of data that occur at the same point. Okay, so in this image on the right-hand side, I have wavelength on the x-axis. I have signal on the y. So what that means is at every particular wavelength, I took a signal measurement. This particular spectra has a peak happening in like the first third of that spectrum. And so if I take all of these measurements, right, this first set of dots that all took place at the same wavelength, okay, and I average the signal, and I do that across the entire spectrum, I will end up with what we call an ensemble average spectrum. Okay. So if we talk about what this looks like in terms of a little bit of a mathematical formula, the average signal is equal to the sum across, the sum of individual spectra, and of an individual spectrum across all spectra, right, divided by the number that you have. If you think about the average signal defined this way, which is what we just said over here on the right, that means that the root mean squared noise, or I should say maybe the variance of the noise, is equal to the sum of that instantaneous signal minus the average signal squared over n, right? So this would be the variance. The root mean squared noise would be the square root of both of these things, right? So root mean squared, so I should probably just call this mean squared. So root mean squared would look like this. So the sum of s sub I minus s sub x squared over n. The square root goes all the way down. Okay. So the total variance here, total variance, is equal to the number of measurements that you make multiplied by the variance that you see for the mean squared noise. Okay. So this tells you two things. The more measurements that you make, the less noise that you'll have, right? So let's sort of break that down. So that means if I take the square root on both sides, I'll end up with square root of n over RMS, or sorry, multiplied by RMS. I can do some fancy algebra and say that this noise that I'm seeing, this the total noise that I'm seeing, okay, I can represent as signal to noise across n spectra. Okay, so that'll be this guy here, represented a different way. Multiply by the square root of n, right? That's this. And I can measure signal to noise of an individual spectra, right? Which is what gives me that root mean squared noise. So I'm just redefining these noise definitions as signal to noise ratios, right? So across all of my, across many spectra for a total noise measurement, right? I've got signal to noise, S over N, for N measurements, multiply by the square root of N. And then this guy over here, because we're talking about root mean squared noise, that's in a single spectra. And so I'm calling this the signal to noise ratio for an individual spectra. And so the usefulness of this equation is that it allows us to estimate, given a certain amount of noise for an individual spectra, how many spectra will I need to take in order to reduce the total noise of that measurement across many spectra, which is what we're trying to do here in the ensemble averaging. So this is a useful equation. I'm pretty sure that in our problem set, I'm asking you to use it. So try to become comfortable with that one. All right, so ensemble averaging is useful because it allows you to extract analytical signal where otherwise it would be hard to see it. There's a couple of assumptions that you're making when you use ensemble averaging. And the first is that you are adhering to the Nyquist sampling theorem. And so let's talk about that a little bit. The Nyquist sampling theorem says that data acquisition frequency has to be at least 2 times the frequency of the highest frequency noise or signal in your measurement, meaning you have to be collecting enough data points, right, to actually see what is noise and what isn't. Okay, so let me sort of illustrate what this might look like and why it's really important. So in this bottom spectra in the figure on the right now you can see that there's much noise, right? It goes up and down, up and down, up and down, up and down, but there's also this low frequency component to this waveform that is sort of drifty over time. So let me change color and maybe pink. Okay, so you can see that this sort of changes over time, right? And there's a little hump there, no big deal. All right, so if you weren't sampling quickly enough, right, you could potentially see, let's go with something different. Okay, blue. If you were only sampling here, 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 you would not want to ensemble average per se, simply because you wouldn't have any way to know whether this like smooth waveform, right, if I connect my dots, were noise or if it were actual chemical encoding or physical property encoding data, right? So the Nyquist sampling theorem says that if you're going to do any sort of ensemble averaging, you need to make sure that you are sampling or making enough measurements in a short period of time in order to know what is noise and what is real signal. All right. In most spectroscopy experiments these days with currently available equipment, it's common to sample at a frequency of about 10 times the Nyquist frequency. This makes sure that you have all signal that's relevant to your chemical system, but you're limiting the amount of high frequency noise that is coming out of that detector. So really what you're doing is you're synchronously, consistently sampling within that waveform. Right. That's, I think, a pretty simple concept. All right, so here's a couple of practice questions that I encourage you to do on your own. I'll post my answers on Brightspace. All right, so then the next kind of software modulation or software methods for getting rid of noise is called boxcar averaging. Boxcar averaging is all right. It's not great. So it improves signal to noise by reducing high frequency variation in a waveform. So we're getting rid of high frequency variation. So you're making a couple of assumptions here. And the first is that the signal that you're looking at is of low frequency. And you have to consider that it's true that the average number, the average of a small number, I should say, of adjacent points is a better measure of signal than any of the individual points. So you could imagine, of course, that if you had high frequency noise here, it would be much easier to say, what's the average across this span? Put it right here in the middle. What's the average across this span? Put it right here in the middle. Right. So it's a great way to limit high frequency noise. It's not great. So let's back up and I'll move some of these drawings. Notice that it's a color. Okay, not that color. Notice that this top unfiltered spectrum, if I sort of connect to the dots using a highlighter, right? There are some things that who knows, because it looks like we're not nowhere near the Nyquist sampling limit for this data set. There might be some useful signal up here that when we boxcar average. So let's smooth everything out. Right? Indeed, we do have a more smooth spectra down here in the bottom, but who knows if this up here was useful? It might have been, but now it's definitely gone. Okay, so details are easily lost, which is sometimes, pretty detrimental to the way that you are using your data. A couple of other different ways that some of we've already talked about. Ensemble averaging. We call these digital filtering methods. Fourier transform is one we'll talk about next week. Here's a quick sketch of it. If you're familiar, great. If you're not, stay tuned. As we talk about spectroscopy, this is really, really, really common in things like IR. We'll talk about it next week too. It's just a method of convolution or deconvolution of your waveform that allows you to apply a smoothing function to get rid of high frequency noise. We will talk about least squares polynomial smoothing in just a minute. So here we go. Oh, I guess in 2 minutes. So the first one I'm going to talk about is moving unweighted average. So I want you to consider the plot on the right. There are 11 filled in circles that indicate original and noisy data. So if I fill them in, I'm just going to connect some dots here. Okay. Here's the original data for this data set. So as you can see, relatively noisy. Okay. What happens is you actually average a particular number of samples. Okay. So the triangles are the unweighted average of the first 5, I think. Yes, a 5-point moving average. The first 5 data points. So that's, let's see, different color. 1, 2, 3, 4, 5. You take the signal average of those 5 points and you stick it in the middle of where those 5 points actually took place, right? So here's the first point, here's the 5th point, and so the X value for this new Y value happens in the middle of that 5 point moving average. So notice that you always have to use an odd number of points in your moving average. The same thing happens for the next set. So instead of including the first point, now I'm going to do this in a different color, not red. Oops, that's not going to help. Let's do this in blue. Okay, so for the second one, you're going to include 1, 2, 3, 4, 5. Okay, and again, now your points span this range in wavelength. So you're going to put your new Y value right in the middle, and it's your new Y value is an average of these 5 blue points, right? And so you just kind of continue to move down and sort of register over one data point for this moving unweighted average. So from the original data that's outlined in yellow to the smooth data that's in blue, the original blue from the text, you can see that data distortion is like pretty significant here, right? You're smoothing your data, but it is pretty significant. And so if you have low frequency data that is, I would say even like relatively low frequency data, it's kind of dicey to use this sort of average. So the fix for this is to use a least squares polynomial smoothing method. So also this is called sometimes Savitsky-Golay. So basically what you're doing is you're performing a least squares fit to a small section of data, and you're fitting it to a polynomial instead of, right, like if you're taking an AChem class and you're thinking about, well, yeah, least squares is what I use to fit a linear equation to my calibration data. Like, realize that least squares is just a method to reduce the deviation of a mathematical equation, or so reduce the deviation of empirical data to a fitted mathematical equation. It can be fitted to any sort of mathematical equation that you can come up with. So a polynomial is a perfectly good choice for this. So basically, you are performing a least squares fit to a small section of a polynomial, and you take that newly calculated midpoint as your smoothed data. Okay, so Savitsky-Golay came up with a series of convolution integers, basically magic numbers, that accomplish the same thing without the work of fitting your data. And so basically what you're going to do is multiply the convolution integer by the signal intensity for a range of data points, sum the products above 5 points, and divide by a normalization integer. So the result is a smooth or new amplitude centered data at point 0. Let's explain it this way. So let's say, I'm gonna use a different color here. Let's say I would like to, so in the most previous slide, we looked at a moving unweighted average, right? And we said we took a 5-point weighted unweighted moving average. This does the same thing, okay, but it's basically a weighted average fitted to a polynomial. So you have 1, 2, 3, 4, 5 points, okay? The point that you're actually the most interested in, that midpoint, okay, is the one that has the most weight. That's why its convolution integer is so high, okay? Meaning it has the most weight, right, in the calculation of the new magnitude or Y value for this point. The ones that are closest to that midpoint have slightly reduced weight, and the ones that are farthest away have a even farther reduced rate. So these convolution integers that Savitsky-Golay came up with are essentially the magnitude of is a numerical, believe empirically derived numerical number that allow you to consistently rank the weight of how, well, this is a terrible explanation. Okay, so allow you to consistently sort of give low priority to points that are farther away from the point of interest. Anyway, it's kind of a cool method. I'm going to ask you to actually apply it in your data problem set. So I'll give you some more info in that problem set. If any of this is confusing, please reach out. I'm happy to Zoom with you to chat about it face to face. All right.